taking this course for credit, I'm writing up some exercises and I'll give them to Professor Izumi, who will post them somewhere. Maybe distribute them. All right, so remind you where we were. We'd started with a subfactor. We'd given tower construction, and we've got some EIs. Satisfying, which were projections satisfying certain relations. We had used these to construct representations, pi, I think we call them, pi, into this algebra. Given by the so-called temporally Lieb algebra, given by the EIs, and pi, sigma I was T EI minus 1 minus EI. T T was related to the index by this formula. And finally, we observed that the trace, these towers of 2 1-factors, and so by the uniqueness of the trace on the two 1-factors is a coherent trace, and we'd observed that the trace of pi of alpha up to normalization depends only on alpha hat, the closure of the braid, which is a link. And let me remind you that if you have a braid alpha, then its closure, this is alpha hat. You have a braid on end strings, and then you tie the top strings to the bottom, you get the oriented link alpha hat. Okay. So that's pretty much what we achieved last time, and we defined the invariant of oriented links to be the normalization. Times the trace of alpha, pi of alpha, where alpha hat is equal to L. So by Alexander's theorem, for every L there exists an alpha, a braid whose closure is that link, and we can define, we know that this trace, if you normalize things right, depends only on alpha hat, so we can define an invariant of links, this formula here. Okay. So that's pretty much where we were at the end of last lecture. Is there any questions on that? All right, so now the first thing I want to do is explore the consequences for this polynomial. I said this basically, the way things work out is rather nice. This is actually a polynomial, essentially in T. I want to explore the consequences of that relation, or which is alternatively the dimension of the algebra generated by 1 and E1 equals 2. If you have a projection, then if you throw in the identity, you have an algebra of exactly dimension 2. And the point is that if you take this element, you can think of that now by this representation of the braid group as sitting inside after pi, as sitting inside the temporally Lieb algebra, so you can square it, or rather, you can take its inverse. We can consider the following 3 elements. This is the braid, this is its inverse, and this is the identity. I'm writing my braid sort of horizontally here, just to fool everyone. Actually, maybe I shouldn't do that. It doesn't really cost anything to write it up this way. this is working in the two-dimensional, remind you what we're doing, n is equal to 2, we're working in this two-dimensional, the braids on two strings. Here's one, here's two, here's another. So these braids are sitting inside this temporally loop algebra, which is spanned by this EI squared equals EI. So since this is only two-dimensional, these three have to have a linear relation among them. That's all I'm trying to say. So there has to be some linear relation among these three. Then if you do the calculation, remember, we know exactly what these things are. They're TEI minus 1 minus EI. Then you find that 1 over T times this minus T times this is equal to, that's an exercise. Hopefully I'll put on the list. They have to be relations, and when you work it out, this relation here and that definition imply precisely that. Okay? So you remember that what this actually means is pi of this braid. So any questions about what that means? It means in this temporary loop algebra, these elements are related by that relation there. Okay. Now, strictly speaking, that's probably not quite accurate, but okay. So let me say something that is accurate. This may make things a little bit easier. Understand anyway. The fact that this algebra is three-dimensional, is two-dimensional, means that there are numbers x, y, and z. That is true. Now, the consequence of this for the Jones polynomial is that 1 over t times v of this minus t times v of this equals so these numbers might not quite work out to be the ones that I've written on the right, but it's all a question, it's just this normalization. That's really the only difference. So what this means, in fact, is that if you want to calculate the Jones polynomial, you can use this relation. This is a Skein relation. And you can actually use it by an inductive argument to calculate, This sort of deserves a few exclamation marks. So let's follow through the path that we got. We defined V to be this. We took a link, we turned it into a braid, we took the closure of and we took the representation of the braid inside this algebra, and then we took the trace. A long, complicated process. But you see, with the Skein relation, we can forget completely about going through braids and so on, and just simply apply this directly. And the idea is as follows. Inductive argument. If you take a picture, see, any link can be undone. This is the other Alexander the Great who proved this. Any link can actually be simplified completely if you allow yourself to change crossings. Okay? If you allow yourself to sort of cut the string and rearrange the crossings, then you can untie any link. So the idea of the inductive argument is step one, isolate a crossing which, if changed, will simplify. So, once again, we start with an oriented link L. And this oriented link, if you want something to think about, you can choose this one here. Okay, this is some oriented link. Then, right. Interesting. Link is certainly not the one that I intended to draw, but it'll do. By this sort of Alexander the Great argument, somewhere in this mess of crossings, there is one that if you reverse it, if you switch it from over to under, then it will simplify the link, right? So you take that link and apply this relation at that crossing. Then if this is the crossing that you've chosen, then this here, the link with that crossing reversed, is simpler by choice. Therefore, by induction, you already know V for it. On the right-hand side, the crossing has absolutely disappeared. So it's much simpler. So you certainly know the polynomial for that. So step 2, apply Skein relation. And induction. So of course, this is a horribly exponential process. You sort of have to know to apply it. You have to know all of the links up to a certain complexity, and then you get the next complexity by having a slightly more complicated thing. But anyway, it's a perfectly fine argument in principle. In practice, it actually works out quite well, because what happens is when you do reverse this crossing here, typically that will really simplify the link a lot more than it looks. So we might even be able to see this happening on this particular link. I think if you reverse this crossing, it looks like there's a huge amount of simplification occurs. This thing comes through and so on. All kinds of things collapse. So in practice, this works extremely well because it just a couple of steps will get you right down to the very simple links. Okay? So this is a way to calculate V. And if you wanted, you could, since it's a way to calculate it, you could also define it in this way. But in order to deduce its existence, it would be quite hard because you would have to show that this procedure, the Skein procedure, is actually gives you a well-defined result. Right, well, now you see, historically things became interesting because Conway, in a famous paper in 1970, had used a very similar formula to calculate the Alexander polynomial. Which is also an invariant of oriented links, and it's a polynomial. So his relationship was delta of this minus delta of this equals root t minus 1 over root t and delta of this. So the relationship for the Alexander polynomial also has something to do with something somewhere being an idempotent. All right, so just to say in passing, the similarity between this relation here and the Conway's relation for the Alexander polynomial allowed people to develop a two-variable generalization of both. So, you might have thought that this similarity in the relations means that this Jones polynomial is somewhat like the Alexander polynomial, but that has revealed itself to be about as far from the truth as you can get. It sort of just about all they have in common. So in particular, just expand on that a little bit. Let's just think about Jones and Alexander. If you define them by these Skein relations, then they would both look like they were exponential in their computational complexity, right? Because each time you want to change a crossing, you introduce two more links, and then so on. You get a whole tower of links growing exponentially in number. Similarly with the Alexander polynomial. But by another definition of the Alexander polynomial, due to Alexander, the Alexander polynomial is actually a polynomial time in the number of crossings in the length. There's another formula, determinant formula, you can write down for it, and that determinants are easy to calculate. So you can actually, Alexander polynomial is polynomial time. Now, on the other hand, the Jones polynomial is now well known to be NP hard. It's not known to be NP, but it's certainly as hard as any other problem that is NP. So it's, you know, provided P is not equal to NP, it's in a different computational complexity class than the Alexander polynomial. Any questions about that? So I don't want to emphasize, talk about that too much. What I want to expand on a bit is Conway's Skein theory and why he introduced it and why it's so good. So, Skein theory. A bit more about that. Because that will lead us back eventually to subfactors. So, I mean, the idea of this Conway thing, the reason it's so good is it's a sort of divide and conquer strategy. It works out very well for that. So let me just illustrate how this might work with a particular knot. I'm going to draw. Hopefully I'll get this one right. It actually doesn't matter very much if I get it wrong. Right. Those knot theorists in the audience will recognize this as the Conway link, Conway knot, which is a close relative of the so-called Kinoshita Terasaka Japanese knot. So anyway, the point about this is that this knot, if you look at it, it sort of decomposes into two chunks. I'll just ignore the orientation for the time being. So it's sort of, well, actually, you could decompose it in lots of ways, but let's say it decomposes into three chunks. This chunk, this chunk, and this chunk. Okay. And what Conway's Skein theory allowed you to do was to work on these three chunks independently, do some Conway, apply some Conway moves, you know, this reduction, this crossing reduction on each one separately, and then combine the three things afterwards. Okay? So if we think about the structure of that calculation, then what it is there's three disks which are linked together by some strings. All I'm doing is copying from that picture over there. Okay, so I hope you saw how this went. Let me just go a little bit slower. I didn't get it. Oh, where these things come from. This was this. This one here was this one here. This one here, that one there. Here, that one there. This one here, that one there. This one here, that one there. Okay, so with the Skein theoretic point of view, this Conway knot has this sort of tangle structure, right? You can sort of group together all the crossings into lumps, so that what's left outside has no crossings. So Conway gave a nice name to these things. Such a thing, what goes inside this? So let's have a look at this over here. This is getting a bit beyond my fluent drawing capabilities. Up, over, under, down there. Okay, I've just isolated this part. This is called a tangle. Okay. So the idea is that there's some kind of highly non-unique, but people have tried to make it kind of unique. In particular, Bill Thurston did quite a bit of work trying to get some kind of uniqueness into the tangle decomposition of the knot. And it's sort of vaguely related to the decompositions of three manifolds. More than vaguely. This Johansson decomposition and so on. So anyway, there's the idea from our point of view. The Skein theory has given rise to a sort of tangle decomposition. And obviously, once you start decomposing knots into tangles, knots and links into tangles, you're obviously going to allow yourself to decompose tangles into tangles. So, for instance, let's make this a little bit more tangle-like. And do a redraw that knot that I just drew. It's good to get practice in it. Now I want to make it a tangle of it, so I'm going to put it all inside a big disc. I'm going to chop this off, this off, this off, and this off. Put it all inside a big disc. So I sort of want this to be round. I want the strings to meet the boundary transversally. Okay. So if I was extending it, and as soon as you start doing this divide and conquer strategy, you are immediately led to consider this calculus, and you're forced to, and you'll have to program it on your computer if you're doing it seriously. You'll see that that decomposition would give us a nice decomposition of this angle. Okay, so the underlying structure of this tangle is revealed to be this one here. So I've taken this Conway tangle. Remember, this is a tangle. Tangle is just a knot with boundary, if you like. So we started off with a knot with boundary, and then I've decomposed it into all of the knottiness has been collected up into these subtangles. Right, and what's left, I'm going to call a planar tangle. So what is a planar tangle? Well, a planar tangle is this big disk, the output disk that contains the whole tangle, and together with three input disks, 1, 2, 3, and the input disks are all connected to each other by curves in the plane, non-intersecting curves in the plane. So input and output disks. this is what my definition of a planar tangle. It's a input, several input disks, these ones, together with an output disk, which is the thing that will contain the whole tangle. The idea is that this is a structure that you could use to study knots and in general tangles simply by inserting any kind of tangle you like into these disks to give you a Conway tangle. Okay. For some reason, I have trouble making this pass, but it's a very simple idea. I tried to develop it from scratch and show that it's sort of forced on you. You can take any knot, or in general any tangle, and divide it up in lots of different ways into a network of tangles connected by curves that don't cross. Okay? So this is a concept that is just forced on you if you want to take seriously Conway's calculation of the Alexander polynomial and the corresponding calculation of the Jones polynomial. Right? You could do anything you can do with that Conway could do was immediately available for the Jones polynomial and this Humphrey polynomial generalized. Right. So I've left a few things out. This was my first shot. I need to tell you, put a bit more structure in order to make this work. Okay. And so the first thing, the most obvious thing I've left out is orientations, right? All of this, everything in the Skein theory for Jones, or for Humphrey, or for Alexander, the links were oriented. Everything was oriented. So that means that these tangles at the end have to have some orientation. So if this were oriented, well, anyway, let me not run through it in detail. The point is that it's quite clear that there has to be, all of these strings have to be oriented. Now, a planar tangle needs to have, as part of its structure, some orientation on the strings. Connected by planar curves, oriented planar curves. So if you orient the strings differently, I mean, you could consider the situation where that one's oriented the opposite way, then you get a different planar tangle. And it will accept different oriented tangles when you put it in. Okay, so that's very easy to imagine. Just take account of the orientation. Another thing that is actually, I guess, even more basic is that there is this obvious cyclic ambiguity here, right? You know, I could, if I wanted to put this tangle in here, then why shouldn't I put it in rotated? And you know, this one has 6 boundary points, so I could rotate it 6 times. And if that happened to be coherent with the orientations, there's total ambiguity on where to put it in. So I need to fix that. And the way that I've discovered over the years to fix that is that on each of the edges of the disks, inside and outside, I make a distinguished edge. So, and I do that simply by putting a $sign there. So that $sign simply means that this edge is distinguished. This edge is distinguished. This one is distinguished. And that one is distinguished. So with that convention, now I can freely glue, provided the orientations work out, I can freely glue these planar tangles one into another. I can either glue a Conway tangle into here in a well-defined way, so where, of course, my Conway tangle itself needs to have a $sign, right? That edge needs to be distinguished. And when I glue, I simply match the distinguished region. So if I wanted to glue this one into this, I would just have to rotate that so that the $signs lined up. You know, probably as I've drawn it, I don't have the right thing. It would not give me this angle. It's easy to get it right. So I put the $sign there, the $sign there. Okay. So what I've developed is a calculus for divide and conquer for Skein theory based on a structure of planar tangles. So I can say, well, this knot theory gave rise to this structure. The structure is somehow more abstract than knot theory. I have the concept of a planar tangle, and I've basically told you in words, we've actually developed everything we need to handle this structure. A planar tangle is a collection of input disks inside a big disk, connected by strings, and with orientations. If we were dealing with unoriented knots, then we would need the orientations. But most important of all is these dollar signs. You need to know for each of these disks, inside and outside, where one particular interval on the edge. Okay, that's to resolve the cyclic ambiguity for gluing. So a planar tangle is input disks, output disks, strings, and privileged interval. And of course, once you've got this, you can glue planar tangles into themselves. So there's two things we can put inside the disk of a planar tangle. First one is Conway tangles, and we'll end up with a Conway tangle. We could also have an operation that was closed. We could put in, suppose we had another planar tangle with the right number of boundary points. Then I could simply glue that one there. So inside this thing, I've got another planar tangle, and I've just stuck it in, and we get another planar tangle. Okay. So it's a nice concept. We've got a planar tangle which is sort of capable of acting on Conway tangles or on itself. Okay, so it's sort of like an algebra structure, where you have an algebra which is capable of acting on itself by left and right multiplication. We've seen that a dozen times already. Or an algebra can have a representation, in which case you put, it acts on some other space. In this case, it's the case of Conway tangles. Right. So we could say now, we were forced to take, Conway tangles was forced to take linear combinations. So we could say, let Cn be the vector space spanned by Conway tangles mod isotopy. Isotopy simply means that inside the disk I can sort of push things around and do three-dimensional operations and mod the Skein relation. In order to talk about the Skein relation, this linear combination of these, you're forced to form a vector space. You're forced to have isotopy, and you're forced to have this vector space. You've got no choice. All of this structure is forced on you. Then, what I've discussed says that the theorem is that Cn, these are an algebra over the operad. So these are just words. I'm going to put them in quotes. Operad of planar tangles. So what do I mean by this? I mean simply I mean what I've said so far. Nothing less, nothing more. The planar tangles can be glued one into the other, and the mathematical structure that expresses that gluing is the word operad. And also, Conway tangles can be inserted into the internal disks of a planar tangle, and the mathematical language for that is to say that they are an algebra over this operator. Yeah.
Why do you need a vector space structure?
In order to, well, you could get away with something weaker. I agree. In fact, you know, I could have made this discussion simply with the set of isotopy classes of Conway tangles. Okay. But if you want to incorporate Skein theory, you need to be able to make sense of this. Okay. So that's where the vector space structure comes in. Good question. Sorry? CN. N is, there's one, oh, sorry, yes. Conway tangles with two n boundary points. Every time you have a Conway tangle, it has a certain number of boundary points. For instance, that one that I've drawn has 4 boundary points. But it's obvious that in because what goes in must come out, right? The number of boundary points has to be always even. So if we let Cn be the vector space with 2n boundary points, so we would call an n a 2 tangle. This would be a 2 tangle. This would be a 2 tangle. Then Cn is the vector space spanned by Conway tangles with 2n boundary points, modulo isotopy and Skein relation. Okay. Then the assertion of the existence, for instance, of the Alexander polynomial for Conway is that the dimension of C0 is equal to 1. This is if and only if Alexander polynomial exists. If we'd used the Alexander version, so the one without these 2 coefficients, then the assertion that the dimension of C0 equals 1 means that given any not is the thing that goes inside C0, no boundary points, then modulo isotopy and the Skein relation, it's got to equal a scalar. Okay? So that's that assertion. And also, you know, if you applied a different Skein relation, that's the same as saying if you use this one, dimension of C0 equals 1 says that the Jones polynomial exists. Okay? So this is an important condition, the dimension of C0 being equal to 1. Right? So I hope everyone is with me. Let me just summarize what we've done. If we wanted to use Conway's idea of divide and conquer for calculating polynomials, Alexander polynomials, and say we wanted to put it on a computer, then we are forced to introduce this structure of planar tangle and planar algebra with gluing. The gluing is the main operation, so gluing the tangles is important. We are forced to introduce this concept of planar algebra, where there's planar tangles with no crossings in between, and then there's the Conway tangles, which we put inside the internal disks. Okay? Everyone happy with that? It's a simple concept, and you know, it's just follow your nose and you get it from divide and conquer with the Skein theory idea. And as was pointed out by a member of the audience, you could do this in a set theoretic way without having the vector space structure, but in order to, the only reason for the vector space structure was to incorporate the Skein relation. So let's think about what, if you did this and if you didn't quotient out by the Skein relation, then what would dimension of C0 be? Well, it would be infinite, because every single knot up to isotopy would contribute, but they would all be linearly independent in C0. So C0, forcing C0 to be equal to 1 is equivalent to the existence of some kind of invariant. Right. Now, I'd like to, having done this sort of extended excursion into knot theory, by the way, if you were the reason I chose this particular knot, just for amusement, is if you calculate the Alexander polynomial of this knot, you get 1. So all kinds of simplifications occur when you do this Skein theory, and it actually ends up being equal to 1. If you wanted to do that calculation, you would be best off to do it by this divide and conquer strategy, rather than just the obviously exponential way of doubling crossings each time. Okay, so now we've had this long excursion away from dot theory. Sorry, away from subfactors. Now I want to hit back towards them. For that, I want to introduce a wonderful example of Skein theory due to Kaufman. I guess unluckily for Lou, this turned out to be more or less equivalent to the Jones polynomial, and it was inspired by the Jones polynomial, but I think when he first discovered this, he thought he had something completely new, but it turned out to be Jones polynomial in disguise. But it's a beautiful and extremely elementary way of looking at the Jones polynomial. In some sense, not as powerful as the way that we've done, but extremely accessible. So it proceeds by what you might call the ultimate Skein theory. Okay, so first of all, the one difference from what we've said so far is it's going to apply unoriented links. Unoriented. That's important. We're never ever going to orient the string in this whole discussion. Okay. But it's going to be the most easy Skein theory to actually implement, which, you know, in that, remember, so how did we decide that the Skein relation sufficed to calculate the Jones polynomial? Well, we said somewhere there's a crossing such that if you change it, it simplifies the picture. If you keep on doing that, you're going to get down to trivial by induction. Right? Well, that is really difficult, and you can imagine implementing that on a computer would be pretty difficult. You would have to define a measure of complexity such that you knew for sure when you changed the crossing you'd actually simplified the complexity. Our intuitive discussion didn't really address that. We just appealed to Alexander the Great. So it's kind of nasty. In practice it works quite well if you do it by hand, but to be systematic it's kind of nasty. Now what Lou came up with was the ultimate Skein theory in which you just get rid of the crossing, bingo, it's gone. So the complexity is reduced, and the complexity is simply the number of crossings that you see. Okay? And his Skein relation was this one. In the unoriented world, these two things, you know, are just sort of on an equal footing. And when you see this relation for the first time, you think, but how is it well defined? I mean, you know, just this crossing, how do I know where to put the A and where to put the A inverse? Well, there's a convention. You can figure out your own convention, but I'll tell you my convention. Everything can always... So the first remark is that in this world of not crossings and things, everything can always be shaded. All of the regions, all of these pictures could always be coherently shaded. And by that I mean a shading such that adjacent regions have different shading. And why is that? That's simply because, from what I said, what goes in must come out. There's always an even number of boundary points, and that immediately implies a coherent shading. So let's take advantage of that possibility to define ourselves a convention. If you have a crossing and it's shaded, let's look at this. If this is shaded, then there's a sense of the crossing. There's positive and negative, and this is positive. And the idea is if you think of this shading as actually being a surface and the strings of the strings of the knot are the boundary of the surface, then what you can think of, if you like, is a long piece of paper on either side here, a long piece of paper on either side, and the paper has just become twisted. Well, there's two ways to twist it. You can either twist it that way or the other way. And by convention, this way, by everyone's convention, this way is the positive convention. Right? Because if you're going in and you've got a screwdriver, it's turning positive. Imagine going into that and the screwdriver while you're doing up the screw. If you came around and looked at it the other way, well, also you're doing up the screw, so it's positive. Right? So therefore there's two possibilities here. This crossing could go that way or the other way. And here I'm going to use A. Now, there's two possibilities of so-called smoothing this. You can go like that. And so this one cuts off the shaded region, and the convention is simply you use A when you've cut off the shaded region, and A inverse when you've joined the shaded region. Okay? And unfortunately for me, like the Hilbert space conjugate linearity, I use the opposite, a completely changed convention. I have no fixed convention. I always use a different one depending on the day of the week or when I start. So other people are much more strict about it than that. I mean, I just decided this one right now. I could have decided the opposite one. Just a matter of chance that I chose this one. But, you know, if you look in the literature, it's probably one chosen for all time. But, you know, this, from the point of view of knot theory, this is absolutely fabulous because you just simply take a knot diagram and you just eliminate all of the crossings one at a time and until you get down to no crossings. And what do you see when you get no crossings? You see a bunch of circles after elimination. Of crossings. See this. So all you need to know is what the contribution of one of these circles has to be. Okay? And it's a simple calculation that a circle has to be equal to, has to represent, this is a closed, unknotted curve. If you just apply this calculus and very simple linear combination, you find that this has to equal minus a squared minus a to the minus 2. Just a consequence. So therefore, if each of these circles contributes minus a squared minus a to the minus 2, then these four of them would give you altogether minus a squared minus a to the minus 2 fourth, and therefore you have an explicit formula for this Lew's thing, and Lew's thing is called the Kaufman bracket. So let me say that again. Given a linked diagram, any linked diagram, this time unoriented, let me sort of more or less do it in case. Then this, the Kaufman bracket is a nice notation reminiscent of the Dirac, Bras, and Cuntz. The Kaufman bracket of this would be equal to, so I'm going to take each of these crossings and I'm going to resolve it according to my Skein rule into 2. So this will be 4 terms, right? There'll be 4 terms. 2 of them coming from here, 2 of them coming from here. Let me start writing them down. According to Lew's notation, the first one, this will be, luckily I've got it right, so this will be A times plus A inverse times this. Now this one has got this resolution. It's the same. This is plus A inverse times the other one. I think I've done that right. Yeah. And then to get the whole expression, you simply do apply this here and here, and you get 4 terms. And then you, for each of these closed circles that you get, you just throw in this factor. You get some polynomial. A. Laurent polynomial. That's called the Kaufman bracket. Well, what Lew observed was, and it's a sort of trivial, easy to prove, is that the Kaufman bracket, this is invariant under Reidemeister moves of type 2 and 3. So these are the moves that do this. That's a type 2 Rhodomeister move. We don't have to worry about orientation. And type 3 is this braid thing where you do this. Right, so these are the so-called type 2 and type 3 Rhodomeister moves, and it was known what Rhodomeister showed was that three-dimensional isotopy is equivalent to three-dimensional isotopy of links is equivalent on link diagrams to changing by Rhodomeister moves of types 2, 3, and this is type 1. Well, you can do a trivial computation using this Kaufman bracket to show that, and let me just cheat here. This may or may not be right, but morally it's right. Minus a cubed times this. Okay. I reserve the right to have this sign corrected and with its a cubed or a to the minus 3. If you reverse this crossing, it would change the a to the minus 3. A to a to the minus 3. So what Lou has done for us is he's defined an invariant of pictures of knots, which is invariant up to types under types 2 and 3, and changes in an extremely simple way under type 1. Okay, so he's got everything there for a knot invariant, except on the nose type 1 invariance. But it's very easy now to go ahead and take care of that type 1 invariance, and you get a version of the Jones polynomial. So if you add an orientation, you get that the Kaufman bracket of a link diagram is oriented, is a to some power, which you can write down explicitly, the Jones polynomial So let me parse this statement. If you take an oriented link, you can oriented link diagram, you could forget about its orientation and take the Kaufman bracket. And that will be a polynomial A. That polynomial in A is actually A to some normalization times the Jones polynomial in A to the 4th. Now, it's not really that much of a surprise because this Kaufman thing is also an expression of some vector space being 3 dimensional. Linear combination. So what this means, reversing the logic here, this means that the Kaufman bracket is a fabulous tool for calculating the Jones polynomial in a very explicit way. Not necessarily any better, any quicker, but very, very explicit. You can just write it out as a simple linear combination of 2 to the n terms, which is the power of a times the power of minus a squared minus a to the minus 2. And this gets to be called delta. So from now on, the rest of this course, I guess there's not so much of this course left. Delta is going to mean this value of a circle, minus a squared minus a to the minus 2. Just to jump ahead a little bit, it's going to turn up in our connection with subfactors. This is going to be the square root of the index. What people in algebraic quantum field theory call the statistical dimension. Okay? Right, so let me just end the first half of today's lecture by just looking at the slightly modified structure that we need. It's slightly simpler in terms of planar tangles. So if we were talking about Kaufman bracket Skein theory, then what kind of tangles, what kind of planar algebra would we have? Well, there's no orientation. Planar tangle for this is no orientation, right? But the only thing that there is for sure is that around every disk there's an even number of boundary points, simply because what goes in must come out. Right? So the kind of planar tangle for the Kaufman bracket would be one like that, where we have to give ourselves a dollar sign. And the dollar signs just resolve the cyclic ambiguity for for the gluing. So that's what a Kaufman planar Kaufman. You could say this is a Kaufman planar tangle. It's the same as the oriented one, but we've forgotten the orientation. And finally, the final remark I'll make is that what is the Kaufman planar algebra? Kaufman planar algebra that will have Kn, and this is a vector space with 2 n boundary points. Okay, so we define it just as we did for Conway theory. We take linear combinations of pictures, modulo, now slightly different. It's modulo only the type 2 and type 3 Reidemeister moves. So this is linear combinations of pictures with crossings modulo type 2 and 3 Reidemeister moves and Kaufman and this. So this is exactly what we did for as Conway would handle the Alexander polynomial. Now we can very quickly and easily calculate what the dimension of Kn is. So Kn has 2 n boundary points. 1, 2, 3. I better add one, right? My favorite joke here is that you discover in this theory that the probability of an integer being even, a random integer being even, is 0, or certainly not equal to 1/2. Always draw pictures, you've got lots of odd. Just stick them in, you end up putting in an odd number. Anyway, so after applying all of these reductions, we get rid of all the crossings, we get rid of all of the instances of closed circles. Each one just goes off with a vector power delta. So at the end of the day, anything in this vector space can be expressed as a linear combination of pictures, which are simply ways of tying the boundary points together with no crossings. So there's a dollar sign somewhere, and then simply tie the boundary points together. Okay, so if you count them in this case, it will be 5. And this is the Catalan number 1 over n plus 1 dimension. This is one of the standard objects counted by the Catalan numbers is disks with the boundary points paired off in a planar fashion. So this number is the dimension of Kn. Kaufman n space. Right, so these Kns form a planar algebra. Over the Kaufman planar operator. Right. So all I did was I took that concept which had come from Conway and I just translated it into the ambient Skein theory, namely this bracket Skein relation. So we immediately have available a very simple divide and conquer tool and formalism which makes working with the Jones polynomial or the Kaufman bracket transparent, elementary, and easily implemented on a computer. Okay, so we'll have a 15-minute break, and then we're going to go straight back and see what this has to do with subfactors. All right, so I want to get straight back to subfactors as quickly as possible after venturing into this topology territory. And the way I'm going to do it is I'm going to show how these Kaufman diagrams, this basis that we've got of the Kaufman Skein space, Skein module as it's called. Actually, one of the remarkable things in Lou's original paper was that they give a beautiful and simple way of visualizing and manipulating these EI relations. So let me remind you, subfactors gave us these EIs, and we had EI squared equals EI, EI EJ equals EJ EI, 1 minus J equals 2, EI plus minus 1 EI equals tau EI. Tau is one of the index. All right, now we're going to take, the idea is very simple and was sort of staring Lou in the face, of course, is that we're going to take Kaufman diagrams, but we're going to think of them as in a sort of braidy way. We're going to make them look as much like possible as braids. So this means that we're going to take one of these diagrams, which initially had a circle with some number of boundary points with a dollar sign there. We're going to make it into a rectangle, and the dollar sign is always going to be on the left vertical edge of the rectangle. And then we're just going to draw in there a Kaufman diagram. So we split the points into two, so there's as many on top as possible, and then we're going to draw less arbitrary, so that it's just a simple topological distortion, a combinatorial distortion. So there's the same number of diagrams here as there are here. So it'll be Catalan possible configurations that we can put in here. But taking a cue from braids, this is obviously the basis of an algebra. And we can think of this algebra in two ways. We can just think of it as like stacking of braids. So let's take this element and let's, just for fun, let's square it. Multiply it by itself again. Right, and then we remove the middle bar, and this becomes so we've defined in this way associative multiplication on these Kaufman diagrams, given this particular choice of dollar. And of course the point is that when we do this concatenation, we might actually have come across some closed circles. We'll just throw them away and count this multiplicative factor of delta. So for instance, on the middle I could have seen this meeting that. We just throw those away and count delta, as we saw with the Kaufman bracket. So we get an algebra. And let me just say in passing, a more savant way of defining it would be to say that, go back to the planar algebra picture, and the dollar signs here. This planar tangle defines the multiplication in the algebra. Well, why is that? Well, you have the right to put in something here, you put in something there, and you get out another D2, D3. So this D1, D2. So we've taken this algebra structure and we've interpreted it simply as the property or the existence of a certain planar tangle in the Kaufman planar operator. So to say bars and so on is a very physical picture, or to say take this element of the operator is actually completely equivalent. It's sort of interesting in that when you take this point of view, you see, well, these planar algebras are actually going to have lots and lots of different algebra structures, because you could imagine other tangles that have similar things. But anyway, coming back to the road to subfactors, there's obvious generators corresponding to the braid groups of this algebra, where you simply, all of the strings go down except between the I and I plus 1th element, where they're like that. and I plus 1. And we're going to call this E sub I. And we do the calculation about what sort of relations they satisfy. Well, let's do EI squared. So let me forget the boundaries for a second. So if I square that, what happens? I multiply by another one on the top. And I get delta times EI. Right? Let me do EI plus 1. EI plus 1. And EI. EI plus or minus 1, a symmetric EI is equal to EI. Finally, it's completely obvious that EI EJ equals EJ EI 5 minus J is equal to 2. Okay, so look at that. That's fantastic. We have produced in this Kaufman diagrammatics some very concrete elements, natural basis elements, satisfying these subfactor temporally relations. Okay, so we have now a diagrammatic way of understanding just the normalization, understanding these operations in terms of these pictures, and the formula is just EI corresponds to 1 over delta E dot. Right. So this suggests that maybe these planar tangles have something to do with subfactors. Because where did we get the little EIs from? We got them from this tower, okay? And then we've seen by this convoluted walk-through knot theory that they turn up as planar pictures. So let's take that seriously, and this is one thing I wanted to do. Perhaps we can apply this theory that Liu developed with these planar tangles and so on, not to just the EIs, but to more structure that we might get from a subfactor. All right. So now I'm just going to briefly abandon this knot theory point of view and go back and tell you a little bit more about subfactors. Okay? And you'll see them, but it's very strongly motivated now. We want to apply these planar tangles to more than just these EIs. So what is there more than the EIs? So that's the question that I'm now going to tackle. What do subfactors have more than just the EIs? So now we're going to have a fairly extended subfactor period. Well, I've sort of alluded to this before, so let's remind ourselves of how we got the EIs. We had N contained in M. Then we did a basic construction, and we got ME1. We call this one M2 for various reasons. And then M3 we got by taking M2 and adding E2 and so on. Out of this tower, we got the EIs. But so let's go back to the tower. The tower is N contained in M, contained in M2, contained in M3, contained in M4, and so on. This one was M0, and this one was M1. The rest of the tower was defined by this second order difference equation using the basic construction. Remind you that Mi plus 1 equals Mi Mi minus 1. Okay? Now, all we've extracted from this so far was just the EIs. We said, oh, we've got these EIs, let's play with them. That gave us a proof of these restriction on the index values. It gave us a knot polynomial. It gave us, and we interpreted it all with this Kaufman diagrammatics and so on. But it was very wasteful. It was very wasteful. Much more information here than just the EIs. So let's see what there is. Well, one of the remarks that I made and you know, was embedded in all of this combinatorics is that the algebra generated by the EIs was finite dimensional. Algebra E1 up to En is finite dimensional. And that's why there's all of this combinatorial structure to it. It's a bit less than you might think because it's a C-star algebra, so it's semi-simple. So there's a lot of combinatorics, but it's very elementary. So what is finite dimensional in this whole picture? What is finite dimensional? Well, it's a very simple thing that's known, you know, since the dawn of time. And subfactors von Neumann would have said it's completely trivial if he'd seen it, which is that if n is contained in M has finite index, this implies that the dimension of n prime intersect M is less than infinity. Okay, so when we did this tower, this one had a certain index, this had the same index, this had the same index, same index. So the index of this in this is just this first index to the power of 4. Right, this one squared, cubed, to the power of 4. So in fact, all of these inclusions in the tower have finite index. So therefore, the n prime, the following things have okay. Okay, so and this is just, you know, this is just the most elementary thing you can imagine in subfactor theory. Prove it, I mean, just if this relative commutant were infinite dimensional, then it just forces the index to be infinite. It's just obvious. So, I mean, in group theory, you know, just does have to be infinitely many cosets. So this is a sort of a priori reason. You don't have to do any combinatorics of counting words on the EIs. You immediately conclude that this is finite dimensional because it's contained in this. EIs, this contains E1, E2 up to EK minus 1. This was the very property of the basic construction that when you add one E, it commutes with everything that was 2 steps down. So when you add the E3 going in here, it's not just in N prime, but it's in M2 prime. So all these E's in the commutant, so they're all sitting in a finite dimensional algebra. So we had an a priori understanding that this algebra was finite dimensional. Okay. But you see, it may or may not be the whole thing. May or may not be the whole thing. If you take the example, the simplest example where it's not, so example, well, you may have forgotten, but this, when I put 2 primes, that means von Neumann algebra generated by, and in finite dimensions, it simply means algebra generated by. So the algebra generated by this is not, it's strictly okay. Okay. As soon as we've got an example of this, we'll see that we will have been wasteful. Let me remind you, all we've done up until now is just take the EIs and look at them. But there's this possibly bigger finite dimensional algebra, which is around, which is available. So let's go to the non-trivial example where n is the fixed points for finite group action. This is the Galois theory example. then it's certainly contained in the Japanese schools, Nakamura, Takeda, and so on, work, one form or another, that interpreted in this way, that n prime intersect m2, so this is when you throw in one EI, this is actually isomorphic to the group algebra, C of G. Okay, this is via a construction known as a cross product, which I have not done, and I'm not going to do because of lack of time. Okay, but C of G could be, the G could be an arbitrary big finite group, so this could be arbitrarily large dimensional, but the algebra that we're looking at is just 1 in E1. Okay, so if you like, what we've done so far is we've taken this example, all that we've extracted from it is this little thing here. Okay, whereas we had available the whole group algebra. So this strongly suggests that we should associate an invariant with a subfactor, which is much stronger than the index, much stronger than just the temporally leave thing. In fact, is these so-called relative commutants. So the tower of relative commutants. Now, if you express it in terms of bimodules and so on, this has a very homological flavor. So let's just not go there. So we have n contained in m, contained in m2. We have n equals m naught. Then we're going to define the tower n prime intersect mi. And for algebraists who still haven't got used to this prime sign, we would say that this is the centralizer mi of n. So I'm not sure whether an algebraist would put the mi there, the n there. Anyway, it's the centralizer. This notation for the same thing. Anyway, it's a tower. Obviously, each one is included in the next one, but this is finite dimensional. So this is finite dimensional. So we've come away with, we've all of a sudden got a tower of finite dimensional algebras. The dimension is going to be growing as I tends to infinity. It obviously contains a canonical copy of these EIs. At this point, I'm going to cheat magnificently and avoid a whole lot of discussion of finite dimensional polynomial algebras, and simply going to give you a theorem which will tell you about the structure of these. So there exists a graph. So we've given a subfactor of finite index. There exists a pointed graph gamma star. So it's a graph in the usual sense of graph theory, and star is a privileged vertex of it, so that we can actually identify this algebra n prime intersect mi. It's isomorphic as a star algebra. A combinatorially, very simply definable algebra defined from a pointed graph. So this is the algebra spanned by loops of length 2i starting and ending. So what do I mean by, how does that become an algebra? Well, first of all, it becomes a star algebra. So this is very unfortunate, the stars. There's too many stars. Star is this privileged point, and it's also a star algebra, so star has two meanings. Actually, once upon a time in the game, that privileged thing in planar tangles was also denoted star, but that was really too many stars, so I introduced the dollar sign. So we're going to have to live with two stars. So if we have a loop star equals the loop read backwards. So if you have some graph like this, I should actually say it's a pointed bipartite graph. So let's get ourselves a pointed bipartite graph. There's a nice pointed bipartite graph with that star. Then a loop. We're going to look at loops. So loops are just walks on the graph that go for a walk on the graph. 1, 2, 3, 4, 5. They're necessarily of even length, right, because of bipartite. So length 2i is necessary. You won't get any of any modeling. And in order to multiply them, you simply do the following. You think of one loop, here's star, and here's another one. So this loop goes off to some point, halfway through, halfway point, and then it comes back. And then you have another one, which goes to its halfway point. So this is loop 1. This is loop 2. And you say that almost always this product is going to be 0. It's only going to be non-zero if the second half of loop 1 is equal to the first half of loop 2. And in that case, the product is, you just forget these, and the answer is this one. 0 was, let me write this in a fancy way, is the Kronecker delta of the blue paths times what you would get by concatenating the yellow paths. So if the two blue halves are equal, then the halfway points are necessarily equal. So I just go out along the first loop and then back along the second loop. That's a manifestly associative operation. It's exactly matrix multiplication if the graph happens to be this graph here. These are matrix units for the algebra. These loops are matrix units for the algebra. Okay, so this is a very simple combinatorial construction, very well known in semi-simple algebra, rediscovered every 10 years or so and called someone's name. People who've associated with this. Anyway, I'll get into that. But anyway, the point is that there is this graph, and the algebra n prime and sec mi is this very concrete algebra of linear combinations of loops. So this graph gets a name. It's an invariant of the subfactor. It's obviously unique, and it's called the principal graph. I discovered it very early on in the game, but then it was properly understood by Ocneanu, who also gave it its name. I'm cheating, as I said, I'm cheating. I'm just saying it exists. Therefore, it's this, going into why it exists. It's not terribly deep. So that's one thing. So we better have some examples right away. Well, the first example is if been stressing that the interest of what we're doing is that there's much more available from a subfactor than just the EIs, but we should know what's going on if there isn't. So let's suppose that that this is true, that there's nothing, that these relative commutants, this tower of relative commutants, this sort of homological derived tower, is nothing more than just the EIs. Okay? And we better know what the graph is in this case. And this is an exercise that can actually be done. Is that the graph is following. Graph is A infinity. Well, in fact, the story is slightly more interesting than that. This is the case if the index is bigger than 4. And if the index is 4 cos squared pi over n, then we get the Coxeter graph A sub n minus 1. So there's two regimes, as we expect with subfactors, the regime less than 4 and regime bigger than 4. They're all related to these A n Coxeter graphs. If the index is bigger than 4, we get the A infinity Coxeter graph, but if it's less than 4, we get truncations of it. We get these A n minus 1. So we immediately see, as I said, this is a calculation that one could do without all that much difficulty. And we immediately see that there is a dichotomy into gamma finite and gamma infinite, corresponding to the first order into something bigger than 4 and something less than 4. So this gets to be called finite depth. Once again, this is an Okeanu infinite depth vocabulary. It may have been Okeanu and myself. We had a discussion about that name. Anyway, that's the name that has come to be associated with it. Finite depth means that this graph is finite. Finite infinite depth means that the graph is infinite. And in the finite depth case, it's obviously nicer things are going to happen. The first nice thing that happens is that gamma squared is the index. Gamma, this principal graph, what do I mean by the norm of a graph? I mean, take the adjacency matrix and think of that as a finite dimensional map between Hilbert spaces and take its norm. Norm in the Hilbert space sense of adjacency matrix. Sort of, one thing that it determines, of course, is the asymptotic dimension of these n prime intersect mi. Another way to get the index is to say how fast does the dimension of n prime intersect mi grow? Well, it grows asymptotically, like some number to the power of I, and that number is the index, and that's easily derivable from this thing here by counting paths. So, any questions about that? Yeah.
Infinity graph means vertex is infinity.
Vertex is right.
Oh
yeah, I didn't say it. There's always only finitely many edges between any two vertices.
Edge is also infinity.
Yeah. It's always connected. It's always connected. Yeah. So maybe it's connected.
Between two vertex, there are infinity edge.
Between two vertices, there's only finitely many edges. Connected, locally finite. So I'm just so used to it, I forget that people even think about other graphs. Actually, the connectedness is interesting because that has to do with it being a factor. we were doing this theory and we were not dealing with factors, then we would have principal graphs that are not connected.
Excuse me. This theory calls for two answer factor.
Yeah.
Any version of type 3?
Yeah, sure. There's the same thing in type 3. I mean, the reason I haven't done type 3 is that we haven't really discussed type 3 factors at all. The reason for that is simply that no time. I was ridiculously ambitious in what I wanted to cover in this course. It's really, at least to actually do, even without the details, it's a semester-long course, right? Even with not proving any theorems, just explaining everything would be a full semester-long course. Okay, everyone happy with that? There is this graph. I just made this assertion. And, you know, it's a combinatorial object, so it's going to play a big role. So let me just say a few examples of what the graph can be. So the first theorem, the first example is when the index is less than 4. Right, so there the principal graph has to be a graph, gamma, whose norm squared is less than or equal to 4. So let me restrict this discussion to finite depth. So I'm assuming everything is finite depth. Then we've got a finite graph whose norm squared of the adjacency matrix is less than 4. Well, it's known in some form or other, going back to the early 20th century, and in some sense even before that, that there is a finite list. Well, you can list these graphs. These are precisely the ADE Coxeter-Dinkin Coxeter graphs. We have, well, actually we don't know where the star might be, so we have AN, and we have DN, and we have E6, E7, and then E8. Right, so even knowing absolutely no polynomial algebras at all, just from this statement, we can conclude that the principal graph for an index 4 subfactor has to be one of these. Okay? That's great. Answering the question before you even know what the question is. Well, it's a theorem due to Ocneanu that because for me was and remains one of the big surprises about the subject is that not all of these occur. So, in fact, not all the DNs occur, only the even DNs occur. Only E6 and E8 occur. No E7. And the star, moreover, the star is restricted to be this form. So, but it's also part of the theorem. Now there's several proofs. I have one. Izumi and Kawaigashi have one. Ocneanu presumably has one, but we've never seen it. That all of these exist. So, I'm sorry, here. The star, so the star has to be as far as possible from the scene of the action. So there we go. That's the sort of surprising and fascinating answer for index less than 4. For index equal to 4, index equal to 4, well, then it also, goes back to Coxeter and company and graph, it's easy to see from graph theory and root systems that in fact these are they have to be extended Coxeter graphs. And just to cut through the A2n, it has to be bipartite. So A2n twiddle is just you have a circle of these things. And star can be any of them. But here now we have the dn's all exist. There's no restriction on the dn's, and E6, E7, and E8 all exist. And actually, there's also this graph here sticking out. So the extended ones are gotten by simply adding an edge and a vertex to the non-extended ones. And for E6, you add the edge there. E7, you add it there. And E8, as always, is cantankerous. These ones symmetrize the Dinkin diagram, and these ones make it as asymmetric as possible. So you add the vertex there. And for dn's, you add another one there. The an's go in the circle. Right. So that's the list now of all, unlike index less than 4, they all occur. So that's the list for index less than 4. And I'd just like to, I'm not going to go in this direction at all because I have another program to work on. I'll just say that what happens in index bigger than 4 then the smallest index value, so we want gamma to be finite, the smallest index value that's allowed is actually equal to 5 plus root 13 over 2. And this was discovered by Hogerup. And there are two subfactors having this index. One has principal graph. This, and the other one has principal graph. Two subfactors. So if you take these graphs and do your hand calculation, you'll come up with this as the square of the norm. If you were Hogerup, you would do it by hand. If you were most people, you would put it on a computer. Anyway, actually, it's not too, for this one, it's not too hard by hand anyway. But so that's the answer. And Hogerup actually showed, first of all, he showed that there was nothing in between 4 and 5 plus root 13 over 2. And he also showed that there exists, the subfactor actually exists. So that was in the mid-90s. And since then, a lot of study has gone on of this Hogerup itself, just trying to understand it. And it's still ongoing, very much an ongoing study of just this subfactor. Okay? We understand these ADE ones in index less than or equal to 4. They're perfectly under control. They're relatively, one might say, unexciting now. But this guy remains at the center of subfactor theory. It wasn't understood. I think the first major advance in understanding it was made by Izumi, who understood it in terms of endomorphisms of the Cuntz algebra. Now these are terms that I'm not going into, but let me just say that he introduced, so as I said, this was Hogerup's original construction was very combinatorial. He basically, if you like, he took the algebra, a way to say this, he took the algebra of paths on this, the algebra of loops on this graph and just exhibited by hand a subfactor in both of these cases. But Izumi introduced a very cunning a totally original, new way of looking at it and constructing this algebra. And then later on, using my planar algebra tools, a student of mine, Emily Peters, managed to actually push through a different program using planar algebras. Which I'm going to get into very soon. Came up with a different construction of the H-group, which allows us to understand it, gives us some understanding of it in terms of, Conway Skein theory and such concepts that come out. So there's these two really quite different, but constructions that somehow add to our understanding of the existence of the H-group subfactor. The gap between 4 and 5 plus root 13 over 2 is actually nowadays rather easy to get. Okay, so that's just a very introduction of a quite big ongoing subject in which a lot of people are involved. The Izumi tool and the planar algebra tool are both used as much as possible, and other tools, some things coming from number theory and so on, part of a large project aimed at building up, going beyond index 4 as far as possible with this method. Izumi, since the type 3 factors were invoked, I should add that the Izumi method uses in an ultimately crucial way this sort of, not necessarily type 3, but an infinite from limit algebras in the construction. Somehow infinity, and the fact that infinity is the same as a smaller infinity is in there. And it seems to give Izumi some special insight that you don't seem to have if you stay in the finite world. All right, so I have 5 minutes to finish off. So let me just state a theorem, and I'll come back to it at the beginning of next time, say some more about it. So, and let me cheat a little bit, so I won't say it quite accurately, and then the first thing I'll do next time is to make it slightly more accurate. There's a duality going along which I haven't talked about at all, so I'm going to just ignore it and pretend that this is statement is correct. Let me call that first approximation. The planar algebra structure. What I'm going to say is actually wrong, but although it is correct for certain subfactors. So the theorem is wrong, but the n prime intersect mi form a planar algebra over the Kaufman operator. So people who know exactly how I'm cheating, but it's a sort of mildly innocent cheat. So I'll say wrong, but correct it next time. Even there, I'll say maybe I won't do other things. So the idea is simply that this is just what it says. If we go back and we take one of these Kaufman tangles, let me just give you one with the ingredients. then this theorem says that I can put with the dimension planar algebra P guy. Remember, a planar algebra is a vector space for each dimension, right? For each number of boundary points, even number of boundary points, you have that, and you get to put elements of that space of the planar algebra in here. So into this you would put x, y, and z. X would belong to P 1, 2, 3, 4, 5, 6 divided by 2, which is 3. Y would belong to P2, and Z would belong to P 1, 2, 3, 4, 5, 6. Let's add a couple just for fun. P4. Right, and this is nothing but n prime intersect M3. This is n prime intersect M2. This is n prime intersect M4. So you put elements of these relative commutants in here, and you get out something. This is supposed to be in the sense of Conway tangle. Remember, you put in tangles, you get out a tangle. This is supposed to be an element of P. Someone tell me. What's the integer that I've got to put in here? Hopefully not everyone's asleep. Put in tangles in here and here and here, and we get out a tangle corresponding to the number of points on the boundary, half of that. So it's P3, I guess maybe everyone's shy. So that's what that's the input, and this is kind of a very useful, important theorem, and it contains somehow, rolls up together a lot of algebraic structure. For instance, let me end with this. The n prime intersect mi are algebras. By their very construction, right, they were the relative commutants of algebras inside other algebras, so they're algebras. And the algebra structure is given, as you would guess if you'd been following along, by the following tangle. We have this n strings here, n boundary points. So this particular tangle allows you to put an element in here, and an element there, and you get out AB. So, and you can also see the EIs. The EIs are the Kaufman pictures, and so on. So this theorem realizes the dream that we had after the interval. The dream that we had was to try to extend the Kaufman and knot theory calculus, Kaufman-Conway knot theory calculus, to all of an arbitrary subfactor. And we've done it. That's this theorem. So it's kind of, it's to be expected to be quite a useful in practice and in theory tool for studying subfactors. And now we have this completely different picture of the subfactor as being these sort of objects with sticks coming out of them, which you can put in these diagrams, and then modulo some Skein relations, where Skein relations are now going to be much more general than the Skein relations in knot theory. Okay. So next time, since it's the last lecture, I'm just going to, I have a goal that I want to get up to some, 2015 work. This is still really back in the 20th century. Just leaving the 20th century. But so I'm going to skip a lot of the discussion of this. I'm going to come back and talk about this theorem once again. But then I'm going to talk a bit about planar algebras and get into situation where we can get unitary representations of these Thompson groups of piecewise linear homeomorphisms and sort of back to knot theory. We can actually represent all knots and links by these piecewise linear homeomorphisms of the interval. Round off the course. So we've done pretty much everything I plan to do except type 3. So unfortunately, the result of this lack of time is that I haven't been able to present Izumi's work, but you have Izumi right here, who can tell you about his wonderful work, and you should ask him to. I bet he's never even given a course on this Cuntz algebra approach. Never given a course. You should all get hold of him and say, you have to give us a course on the Cuntz algebra approach to subfactors. Right, so see you on Friday.